I will introduce our next and last speaker one more time. His name is Djordje Hirsch.
Yeah.
Sorry, Djordje Hirsch. Data science manager at Yettel. He is an experienced machine learning expert focused on AI application in telecom industry with a strong engineering background and a master's degree in electrical and electronics engineering from University of Belgrade. He will talk about application of AI in early melanoma detection. Djordje, the stage is yours.
Yeah, thank you very much. So I was already introduced. I'm working in telco business. This is my core interest. This is something I'm living from, but during my PhD studies, I want to do something else. I want to find some application in healthcare. I read a lot of papers where this computer-aided diagnostics brings additional value and helps and saves lives. So first of all, I decided to focus on this melanoma problem. So let me check if this works. Okay. So what is my main motivation here? According to many papers, a lot of authors are saying that melanoma has epidemic increased number of diagnosed cases and unfortunately deaths. There are some predictions where in following 20 years we can expect a 50% increase in the number of cases and in number of deaths, unfortunately. So it's like a 17th most deadly cancer, but again, it doesn't sound much, but when you see this number, this is not just statistics, these are lives. So if we go a step further, okay, we can expect a lot more cases, unfortunately. What is the survival rate there? So in early detection, survival rate is very high. It's over 99% in 5 years period. So again, if it is localized, if this malignant change is spread across the body, survival rate drops about 30%. So it's very important and very significant to identify it on time. So what is the treatment? For these early stages, 0 and first stage, we can expect, again, about 99% survivability in 5-year period. Even for second stage, it is 94%. But all other stages, all of these 3 stages can be successfully treated on surgical way, just removing this malignant change. But if there are some metastasis, I lose it. So in some later stages, 3 and 4, some additional treatment, like chemotherapy and some advanced medication, should be applied with significantly lower success rate. So these two takeaways are there are going to be more cases and early prevention, early detection is very important. So next question is it possible to visually identify malignant change and what is the success of this screening? So for this visual screening is performed by dermatology specialists using this dermatoscope, this small device, for ones who don't know, optical device which magnifies this skin lesion, and usually it could be integrated with a digital camera where this change could be stored and later be a part of some other analysis, or if you want to track history, it could be done by these digital images. So what are the criteria of diagnosing this melanoma change? One of the most popular and well-known method is this ABCD rule, where again some visual characteristics of melanoma are extracted. So you may see from this picture that there is a symmetry, border, color, diameter, and involving. So you have to have this time element to see if this change on skin is evolving. There are some additional one, like this 7-point checklist and cache and many others. But the key takeaway here is that basically this visual screening can detect some suspicious changes, and definitely this one could be treated further on by surgical removal and later on pathohistological analysis. But again, all of these methods are not 100% accurate, and even with this pathological analysis at the end, it is not certain if something is malignant. And it's still challenging for dermatologists, for a group of dermatologists. Even if we have this conciliar opinion, it's still not 100% sure. So we now know that it is possible to visually identify potential threat here. Oops, I'm having trouble with this one, sorry. So what images can we access and what images can we use in this, let's call it project? So there are some private data sets, but it's very hard to collect it. It's very hard, like from ethical aspect, from privacy aspect, and from many other aspects, especially in our country. So good starting point is to use publicly available data sets, open data sets, just to verify your approach and your methodology. So one of the most common and most cited data sets are collected by International Skin Imaging Collaboration Organization. So they are organized by different faculties, by different sources of these dermatologist images, but one of the most popular one is this HAM 10,000. This is, HAM is short, human against machine, and this data set is the most curated one. It consists, as the name says, from 10,000 images of skin lesions, and here what is most important for this data set is that all images are taken with the same camera, with the same dermatoscope. So all of artifacts, all of, let's say, variations in data set with different cameras, with different resolutions, etc., are not present in this data set. And this is very good starting point to verify your approach, because at the end, if you are not getting good results on this data set, then your approach is wrong somehow, and you should correct it. Again, same organization with cooperation with Society for Image Informatics in Medicine made these challenges. They are announced periodically, and the last one was in 2020, I guess, and are hosted in Kaggle competition. And this really brought some interesting ideas, because making open all of these data sets show all benefits of sharing this data. So if you are keeping your closed data set, it is going to be accessed by a very small amount of people. A few papers are going to be announced, but here you may see creativity of open community. They have really interesting approaches. They got really good results. They were using different architectures, different processing of the image, and definitely, as in everything, opening data set is the very, very important stuff, and this is the proof that some interesting things can happen if the data set is accessible by everyone. On this data set, it's quite bigger. There are 33K of images, and it consists of a lot of variations compared to this HAM 10,000. But again, there is a lot of images, and this is something more similar to real life and real situations which can you face by building this maybe mobile application or something. So beside these ISIC data sets, there are some PH2 or 7-point criteria, what was the name, evaluation database. So there are a lot of available public data, but most of papers are focused on this one hosted by International Skin Collaboration. So during my work, I noticed that some challenges in this data set. First of all, there is high class imbalance, thank God, because malignant cases are in vast majority. But according to this data set, there are a lot of artifacts which bring additional bias. For instance, like a skin hair. These lessons are taken for different parts of the body. So background, skin is different. Sometimes you see wrinkles, sometimes you see hair. Even dermatoscope is introducing some additional artifacts. For instance, you have to put this optical gel in order to take a photo. This gel can make some bubbles. Dermatoscope sometimes leave this black circle, like probably from ocular or something. Usually, but not usually, sometimes the ruler is present on the image because, again, you have to measure the diameter of this skin lesion. So there are a lot of artifacts, and they can all influence additional variations in data set. Especially there was interesting paper my colleague mentioned, I don't know if he's here, that sometimes on malignant, there was a data set with very good results. And the problem there was that the ruler was present on every malignant change. So it like make label leakage and made like this data set perfect for learning and testing. But at the end, there was a problem with the data. So my advice, if somebody wants to do some research on this topic, to start from these publicly available data sets to verify that his methodology is good and this approach has potential to do something better on some real-life data. Okay, let's start with the modeling. We have now data set, we are aware of the problem. How can we approach this modeling phase? So first, there are a lot of papers using this classical machine learning where some random forest, some support vector machine is supported with some, let's say, handcrafted features, some manually crafted features. But again, this methodology is hard to automate and it's not robust enough. So let's try to do something with deep learning. Deep learning has a really good results on this medical imaging, and there are again a lot of papers where it is demonstrated that these advanced models can bring additional value to this melanoma identification or any kind of medical imaging. So I started with convolutional neural networks and the advanced visual transformers. But let's say, number of images was not enough for visual transformers to converge. So again, convolutional neural networks are giving us a better performance. At least for me, ResNet 50 and exception gave me significantly better results from all other networks I was comparing them with, including visual transformers. At the end, there are some papers discussing, because again, let's go step backward, we do not have enough images. So training convolutional neural network from scratch will not bring us very good results because again, it cannot converge on this small amount of data. We should use pre-trained network. And now the question is on what data set we should pre-train it. There are some papers discussing some medical images, some additional data sets, and they're comparing the results with, let's say, the simplest ImageNet data set, general data set. So no significant improvement was done with any medical data set. Best results we're getting from this ImageNet data set, which was like the most common data set for pre-training network, and hopefully all of these networks are easy accessible. They are pre-trained on this data set, and this is a good news because we don't have to manually pre-train some data set. We can use already pre-trained network on this ImageNet data set. Okay, so let's say we selected the model, we selected an approach, we selected, let's say, exception network with pre-trained on the ImageNet data set. Now, next step, which brings a lot of performance increase for me, was augmentation. But again, here we have to be very cautious when we apply it. Because of this ABCDE rule, we don't have to degrade information which is relevant for this prediction. So we must not influence the shape of the skin lesion. We should not influence the color, the contrast, and everything. We should do some. Definitely, performance could be increased, but again, we must preserve this ABCD rule, and we cannot degrade the information which is used for predicting melanoma. So Here, let's say, you have to do a lot of experiments to see what works, what not. And for me, maybe this was the most time-consuming phase where I was experimenting with different augmentations, with different contrast rates, saturations, different cropping of images. So I encourage you, if you are doing this project, to invest a bit more time in the augmentation phase. Again, additional stuff from this augmentation is, again, idea got from this Kaggle challenge. They are using artificially augmented artifacts. So they are putting these artifacts on random images, and this how, by showing this random, like rural, augmenting skin, hair, augmenting these bubbles from gel, you may motivate your model to ignore these changes and focus on more important stuff. This can be easily evaluated by some model explainability, where you can see during prediction that model is not focusing on this skin change, these artifacts, but only on skin lesson. Okay, let's say we now have a model, we prepare data set, augmented it. Additional methodology which brought value for me was localization. When you see this skin lesson, a lot of this image is covered by background, by regular skin, not carrying any significant information important for classifying this melanoma. So you can play with different localization. For instance, object detection. Here, it's very, let's say, you need some manual work to prepare data set, to put these bounding boxes around this skin lesson in order to make this object detection algorithm work. I was playing with YOLO. I got some results with YOLO. There are a lot of papers using RCNN or some other methodology, and everybody got some improvement in the results. Next one is semantic segmentation. Again, labeling for this phase is quite time-consuming. A lot of manual work is required in order to prepare data set for this one. Thankfully, this HAM 10,000 already has included binary labels required for semantic segmentation. But compare these two phases, it's shown that semantic segmentation excludes healthy skin from skin lesson. And it is shown that it can be empirically proved that object detection gives better results because you include part of a healthy skin, and apparently contrast between melanoma and this healthy skin is important for classification. So if you would like to play with this one, I would recommend to do object detection. And during my work, I get like a special effort, and this is the main topic of my work, using this special attention for focusing only on parts of the image where the relevant information is located. So I experimented a lot with different spatial attention models, and basically this should be the main, let's say, backbone of my work. Again, yeah, for attention, you may also have some explainability. You can like visualize all of these attention weights and see where the model is gaining the main information which uses for predicting the melanoma. Okay, so let's say we made the model, we got some results, and what metrics should we use there? It's very hard to compare these models with other papers because everybody is using different metrics. Somebody uses like F1 score, somebody uses accuracy, precision, and like there is no two papers which are using the same metrics. And it's very hard to again, I'm repeating myself, and it was very frustrating for me because you cannot find what is the benefits you are bringing. According to my understanding, it's the most valuable, let's say, the most expensive error are false negatives. So you tell somebody, okay, you are healthy, go home, you don't need to worry, but again, somebody go home with a malignant change on his skin. So we should eliminate false negatives. So recall or sensitivity should be high. And for my experiment, I use like a 95% detecting of all positive cases. So I was using TensorFlow, and TensorFlow has this like metrics, precision and recall. So I put recall to constant value, and I was optimizing for different experiment. I was optimizing precision. So precision definitely can be discussed. What is the acceptable value? But for recall, we must keep recall high, the highest possible. So this was the metrics I used. So precision at recall at 0.95. And basically, this is all I prepared here. Most important one is that sometimes this performance can outperform a single dermatologist, but never a conciliar opinion of multiple dermatologists. And there are a lot of papers which are showing that mortality rates in the parts of the world where with poor access to dermatologists is significantly higher, even 2 times higher than some urban areas with developed countries where like this is a normal annual exam for everyone. So introducing some good computer-aided diagnostics in these areas, we can significantly lower the mortality rate. And I believe all of our work here and maybe some future work will develop this tool which will help save lives in these remote parts of the world. Thank you. Any questions if somebody likes to? Yeah?
So I was just wondering if this is already available to people, like, through the application? So I can
Not
scan
yet, not yet.
So
Again, yeah, it's important. Here we are dealing with dermatoscopic images. It would be definitely better if we can collect a good data set with these macroscopic images, where like individual who at his or her home, like just take a photo of this lesson and immediately get some response if additional care is required.
Okay, so how much time do you think you need to get to the market with this product?
I'm not sure. It's still early phase. I'm not sure how much, but definitely we plan to do something like this.
Perfect. Thanks.
Thank you for the presentation. Yeah.
I must look it. I need object detection.
It was great. I have a questions regarding the augmentation. Did you use some libraries or did you do it manually? And could you share with us like what sort of parameters did you have to like tune hyperparameters in order to get some better results with the augmentation?
Yes, something is done manually. So this like hair augmentation, bubble, some other artifact is done manually. But for like this well-known augmentation, it's performed by this IMG AUG library. It's probably you're familiar with, yeah.
Thanks.
But sorry, I don't know by heart or parameters, but we can keep in touch. I can share with you, no problem.
Yeah, so Consilium might give better results than one doctor. Do you think that maybe using multiple models and having like weighted result or maybe kind of combining the results would give better recall, or from your experiments do they fail at the same places?
Yes, basically this competition I mentioned, like top 3 places were like an ensemble of different deep learning models. They are definitely getting, but I was focusing on single models. It's like more elegant for me, and I really enjoy working on single model, not combining multiple models. But definitely this competition on Kaggle proved that ensemble of different models. They were doing like a voting or something, I forgot. They got like a winning solution.
Perfect. Thank you.
Djordje, thank you
Yeah.
so much for sharing your insights with us.
Oh.
Here is your certificate of
Oh, surprise.
appreciation
Excellent.
for your engagement in
Thank you.
the program. Thank you very much.
Thank you.